The physiological response to aging is not uniform across genders, and this includes the way male and female organisms experience metabolic decline, fat redistribution, and cellular repair mechanisms like autophagy. As research into nicotinamide mononucleotide (NMN) advances, a growing body of evidence suggests that sex differences may significantly influence the degree and nature of its benefits. NMN enhances autophagy by boosting intracellular NAD+ and activating key regulators such as sirtuins and EMPK, yet the expression, activity, and downstream effects of these pathways can differ between males and females. This raises important questions about whether NMN supplementation yields equally protective effects against age-related obesity in both sexes, or whether the benefits are shaped by hormonal environment, fat distribution patterns, or sex-specific autophagy regulation. One of the most consistent observations in aging research is that females tend to retain higher levels of adiposity, especially subcutaneous fat, while males show a greater tendency toward visceral fat accumulation and sarcopenic obesity. These patterns are partly regulated by sex hormones. Estrogen in females promotes subcutaneous fat deposition and metabolic flexibility, while testosterone in males helps maintain muscle mass and insulin sensitivity. With aging, both sexes experience hormonal shifts. Estrogen declines sharply after menopause, while testosterone levels in men drop more gradually. These hormonal changes alter fat distribution, mitochondrial function, and autophagic efficiency, creating a different baseline from which NMN must act. In male rodent models, NMN supplementation has been shown to consistently enhance autophagic flux in liver, skeletal muscle, and visceral adipose tissue, leading to improvements in insulin sensitivity, mitochondrial respiration, and reductions in hepatic steatosis. These effects are strongly mediated by increased NAD+ availability and SIRT1/SIRT3 activation, which tend to be more robust in male tissues, possibly due to higher basal expression levels or lower baseline inflammation. Male mice often show greater reductions in body weight and visceral fat with NMN compared to females, along with more pronounced improvements in muscle oxidative capacity. This may reflect the male-specific susceptibility to NAD+ depletion in central metabolic tissues, which NMN helps restore. In females, however, the response to NMN is more nuanced. While NMN does increase NAD+ and activate autophagy-related signaling in females as well, the effects on body composition and fat metabolism can be less dramatic. For example, studies have shown that aged female mice treated with NMN experience improvements in liver mitochondrial function and systemic inflammation, but only modest reductions in fat mass. One possible explanation is that subcutaneous fat, which predominates in females, is less metabolically harmful and may not respond as readily to autophagy-driven remodeling. Moreover, the decline in estrogen after menopause influences the expression of key autophagy genes and sirtuin activity, potentially blunting the full effect of NMN. That said, estrogen replacement or dietary phytoestrogens have been shown to synergize with NMN to enhance autophagic outcomes in female models, highlighting the importance of hormonal context. At the cellular level, there are intriguing differences in how autophagy is regulated between male and female cells. Female cells often exhibit greater baseline resilience to oxidative stress and higher mitochondrial efficiency, which could reduce the relative need for NMN-stimulated autophagic clearance. Conversely, male cells may rely more on stress-induced autophagy to maintain mitochondrial quality, especially under conditions of NAD+ depletion. This could explain why NMN's restorative effects appear stronger in tissues where damage is more advanced, often the case in aging males. Beyond fat metabolism, NMN's influence on muscle preservation also shows gender-related variability. In males, NMN tends to preserve lean mass and enhance endurance more robustly, likely due to a combination of testosterone preservation and improved mitochondrial turnover. In aging females, the protective effect on muscle may be more dependent on estrogen-sensitive pathways, meaning NMN's benefits are more variable unless paired with lifestyle or nutritional support that addresses hormonal decline. Human data remain limited, but suggest parallel trends. Small clinical trials involving NMN have reported gender balance improvements in some markers, such as insulin sensitivity and NAD+ levels, but differences in fat loss or metabolic flexibility have yet to be fully examined. It's plausible that premenopausal and postmenopausal women would exhibit different responses, as hormonal environment plays a decisive role in both autophagy regulation and energy metabolism. Future human studies with sex-stratified analysis will be crucial for designing age and gender-appropriate NMN-based therapies. In conclusion, gender-specific responses to NMN supplementation appear to be real and biologically grounded. Males may exhibit stronger improvements in autophagic flux, visceral fat loss, and mitochondrial function due to their greater vulnerability to NAD+ depletion and reliance on sirtuin pathways. Females, while also benefiting from NMN, may require complementary strategies, such as hormonal support, dietary modifications, or longer treatment durations, to achieve similar effects, especially in fat remodeling. These differences do not diminish the value of NMN as a therapeutic candidate for aging-related obesity, but rather underscore the need for precision in its application. As we move toward more individualized metabolic therapies, sex-specific biology will be a critical lens through which NMN's full potential can be realized.